ப்ரொஃபசர் லைன்ல இல்லைங்களா ரங்கசாமி?
இருக்காங்க. ரெக்கார்டிங் இன்னும் ஸ்டார்ட் ஆகல.
ரெக்கார்டிங் போயிட்டே இருக்கு, ரெக்கார்டிங் ஆகல.
Okay, we'll start now. Again, this Rangasamy is here. Good morning, everyone. It's my pleasure to welcome everyone to this webinar. And Professor Arnab Mukherjee is with us. Sir, we are looking forward to having you again as a resource person for the second day's webinar. And on behalf of Guru Nanak College, I welcome you, Professor, to this webinar. And I really appreciate our participant for taking interest to attend the second day of the webinar on Introduction to Thermodynamics. And I hope this lecture will be giving a lot to you and have a great session. Now I invite Professor Arnab Mukherjee to deliver the lecture. Please, sir.
Okay, thank you. So I will just start sharing my slides now. Just 1 second. Okay. Okay, I have shared it now. So is it the screen?
Yeah, we can see the slides.
Yeah.
Okay, good.
Okay, good. Okay, so yeah, let me know if there is a problem in between any time. Please feel free to let me know. And I just wanted to know before I start that if there is any question from anybody from yesterday's lecture, so either they can post or you can ask me directly. If not, then I will proceed with today's content. So today's content will be slightly different for undergraduate students because I'm going to introduce statistical aspects of thermodynamics today. After finishing a little bit of the classical part.
Professor,
that's why it may be very different, but again.
Yes, 1 minute.
Hello.
The whole screen is there, sir. PPT is in the background mode. Okay, now it's okay. Okay, sir.
Okay. So I was just telling that I will talk about the statistical aspects of thermodynamics, which is not often taught in undergraduates. There is some background noise, so I would suggest to mute in case there is no question. Okay, so I was telling that they talk about statistical aspects of thermodynamics. It is taught normally graduate level. However, this is very important to understand thermodynamics, especially second law of thermodynamics. Very simple. So it only requires the knowledge of is typically taught in 12th standard. So once people understand the statistical aspects of thermodynamics, it also helps to understand the overall aspects of this particular subject. So therefore, in my class, I always teach both the aspects, and also in NPTEL lectures, if anybody is watching, from 7th week onwards, the statistical aspect of thermodynamics or statistical thermodynamics comes. Although, again, I don't use equations at this level. So typically that is meant for senior student in chemistry. So at this level, even for statistical thermodynamics, it is mostly pictorial descriptions of the things, which probably will help to give the conceptual understanding for this particular subject. So that is the primary goal. Again, in 2 classes, thermodynamics is not possible to be completely, possible to cover completely. However, my objective is to give only the essential aspects of this particular subject without giving the exact details, which again can be found in books and also in my NPTEL lectures or from standard classes. So I try to give something which is different from what is normally taught. For example, so I will start where I ended yesterday. So I started with second law of thermodynamics. Now, when I ask about second law of thermodynamics to the students, some people say that the second law says that entropy of the universe will increase, entropy of the system plus surrounding will spontaneously increase, or entropy of an isolated system will increase. Yes, so there are many possible ways in which second law of thermodynamics can be described, and they are all connected and related. So here I will try to give at least 4 to 5 different statements of second law of thermodynamics, and I will try to show that they are all connected. For example, the first statement that we can start with is the Kelvin-Planck statement. What it says is that it is impossible to construct an engine, not and. It is impossible to construct an engine that operating in a cycle, that is very important, in a cycle, will produce no effect other than extraction of heat from a reservoir and the performance of an equivalent amount of work. So this is pictorially given in this. So it is very difficult to construct an engine which will run in a cycle and it will take heat and completely convert to work. So it is not possible. That's what the statement says. So again, I remember yesterday I talked about there is no free lunch is the first law, and one has to always give a tip to the restaurant in order to come back again. So by coming back again, what I meant is, working in a cycle. If you do only once, it is possible to convert total heat to total work in one step. It is possible. But if you want to do it again and again, then you need to give away some heat to the cold heat bath. And this particular heat is the tip to the restaurant that I was talking about. That you pay for lunch, which is your work, but also you pay for tip. So your total cost is the lunch cost plus tip cost. And that is the input heat. Then only it is possible to go in a cycle. So this is allowed, right hand side, left hand side is not allowed. So this is Kelvin-Planck statement of the second law. And immediately you can see, if you know the definition of efficiency, you can see that in this particular process, the efficiency of the engine will be 1, because your work output is W, which is equal to Q, and your heat input is Q. So therefore it is just 1. So another statement of second law is that it is not possible to make an engine that will have an efficiency 1. Okay. So you see, already I talked about 2 statements of second law of thermodynamics. Now, what is Clausius statement? Clausius statement of thermodynamics is that it is impossible to construct a refrigerator, again operating in a cycle, will produce no effect other than transfer of heat from low temperature reservoir to a high temperature reservoir. That means you cannot take the heat from a cold bath and put it to a hot bath without doing any work. So left hand side is not possible. Right hand side is possible because you are doing some work. Now, this Clausius statement of second law and Kelvin statement of second law, they are related, and one can show the equivalence of that. I'm not going to go into detail of that, but we can show that if we connect, for example, this is impossibility. This is the Kelvin statement, and if I construct a combined engine, one can show that it is coming to a Clausius impossibility. So if you use a Kelvin's impossibility construction, then you will land up into a Clausius impossibility condition. So therefore, if Kelvin is right, Kelvin statement is correct, then Clausius statement is also correct. And same way, we can also construct Clausius statement impossibility, and then we get Kelvin statement impossibility. So therefore, they are equivalent. So this is equivalence of Clausius Planck and Kelvin-Planck and Clausius statement of second law. And so that means we now talked about 3 different statements of second law. One again is that efficiency of engine cannot be 1. Second is that no engine working in a cycle can take heat directly from hot reservoir and completely convert to work. Third statement is that it is not possible to construct an engine that works in a cycle or refrigerator that works in a cycle and takes heat from cold reservoir and sends it to the hot reservoir. However, opposite is possible. You can take heat from hot reservoir and send it to cold reservoir without doing any work. So that is possible, that we know, right? Every day, this thing. So this essentially means that heat cannot be spontaneously transferred from low temperature to high temperature without doing any work. That's why for refrigerator, we need power connection. A refrigerator cannot run. Refrigerator, the temperature inside is 4 degrees centigrade, right? Outside, let's say room temperature, 28 degrees centigrade. So from 4 to 28, heat cannot be transferred without doing any work. And here, how the work is done, we plug it to the electrical socket, which runs a compressor, and that compressor actually cools the refrigerator, and the extra heat is ejected out. Okay, so you see now 3 statements are connected, and then many more can be also said about that all reversible engines will have same efficiency. That also can be shown. Now, what will be the maximum efficiency possible? So for that, in 1824, Carnot, he was an engineer, so he constructed a hypothetical engine in which the first part is an isothermal process, isothermal expansion process, and then isothermal expansion process, temperature does not change, and then a reversible isothermal expansion process, and then an adiabatic expansion process, and then an isothermal compression process, and then an adiabatic compression process, so that it comes to the same point. So you see now it is working in a cycle. Now, if you actually calculate, you will see the complete heat input in the first step is converted to work. So 1 to 2, if you just consider 1 to 2, you will get full efficiency of the engine. However, when you go from 3 to 4, you eject the heat out to the cold reservoir, and that is lost to the reservoir, and then you come back to 1, and the cycle will be complete. So now in the full cycle, you will see that you are not going to get an efficiency 1. So if you calculate the efficiency, you will get 1 minus T2 by T1, and T2 is the temperature of the cold reservoir. Now, only way, I don't have the equation here, but I hope that you know that the efficiency will be 1 minus T2 by T1. Now, only way you can get efficiency 1 is if the T2, that means the temperature of the cold reservoir, becomes 0. But you know that if temperature of the cold reservoir becomes 0, then efficiency will be 1. Then if efficiency is 1, then it will violate Kelvin-Planck statement. So therefore, one can say that it is not possible to reach absolute 0. So therefore, another statement of the second law is that it is impossible to reach absolute 0, because if you reach absolute 0, you can construct an engine that will have an efficiency 1, which means that it will take the heat without increasing the entropy of the universe. It will basically run in a cycle. Okay, so now this particular cyclic process has heat and temperature at that point, right? But when you try to see, so here you see that the work is a path function, heat is a path function. But when you calculate heat by temperature for all the 4 steps, you will see that is actually a state function, because that is becoming 0 when it comes there. So that gave the idea to Clausius first time that one can have a particular quantity called heat by temperature. Of course, we are talking about reversible process here. So heat by temperature, that can be defined as entropy. Or I think the entropy then came later on and all that. I forgot about that particular part. But the point is that this Carnot engine gave rise to a new quantity, that is heat by temperature. So if a process is reversible, then the change in entropy is reversible heat exchange by temperature. And from there, the Clausius inequality that comes is that the change in entropy always will be greater than heat change, not reversible heat change, heat change by temperature. So for example, I'll show you one particular process here. So let's say there are two chambers in an isolated system, and you have gases here. Once you make a hole, the gases will fill the whole box, right? We saw that animation yesterday also, that once we remove the barrier, the gas particles are going to the other side. Now this is an irreversible process, and since the boundary is isolated, there is no heat exchange and all, but we know the entropy is increasing. So you see that change in entropy cannot be equal to dq by t, because here dq is 0. But so the entropy change would have been 0 if we only consider dq by t. But actually, entropy change is not dq by t. It is greater than equal to dq by t, and it is equal to dq by t only when q is reversible. But this is an irreversible process. Therefore, one has to construct an equivalent reversible path connecting these 2 points, which is shown here. And once you do that, once you go from here to here in a reversible manner, you will see that there will be a finite amount of heat input or output there, giving rise to a change in entropy. Anyway, so now if you take two systems at two different temperatures, one can show that an heat exchange will be only possible from high temperature alpha to beta, where and therefore one can show that always one can construct a system in which the overall change in the entropy for a spontaneous process will be greater than 0 or equal to 0 if it is equilibrium, and therefore entropy of the system plus surrounding is always going to be increasing. So that is another statement of the second law. Now so all these different statements that I talked about today, so Clausius statement, Kelvin-Planck statement, then efficiency cannot be 1, all reversible engines have equal efficiency, and then entropy of the universe or system or surrounding is always increasing. You can see now that all are connected. All are corollaries of the second law of thermodynamics. So what is the statistical formulation of the second law now? Now, till now, we talked about reversible heat, temperature, energy, and stuff like that, right? Now, we know that an increase in entropy is favorable. We know that, right? But why an increase in entropy is favorable, that classical aspects of thermodynamics cannot tell us. Because we don't know from all the equations of classical thermodynamics that why if in some process entropy increases, that will be a spontaneous process, given that everything else is fine. So to understand that, we need a statistical understanding or a molecular understanding of thermodynamics. So now I'm going to read some of the slides so that it remains there. So question is that why entropy increase is favorable? So we have learned that entropy is reversible heat change at a given temperature from the classical law. Therefore, it is essentially the heat energy. Then how to relate to chaos or disorder or randomness? Because if I ask you that what is entropy, you will say that it is randomness. Most of you will say it is randomness, that it is chaos or randomness, and that is giving rise to increase in entropy. Now how do you relate a reversible heat exchange divided by the temperature to randomness or chaos? So heat energy, as we have seen, is random motions of molecules, that we know. Heat is proportional to temperature, that we know, and temperature is nothing but kinetic energy, that also we have discussed. Therefore, heat is some random motions. But how then it gives rise to this time arrow, meaning that as the time progresses, we have shown you that as the time progresses, entropy of the universe is increasing. Now, how it is related to that and why it will be favorable? How we know that for a certain events like falling or breaking of an egg, that entropy must be increasing? How do we know that if you drop an ink in a solvent or in water, the ink will disperse? Apparently we don't know that. So the answer lies in the fact that second law, the entropy of the universe is increasing, is true only on an average. That is very important point. The microscopic motions may have microscopic motions may have reversibility. It can go against the second law for a small amount of time or for a brief processes. But on an average, it must follow the overall process that entropy will increase, or entropy of the universe will increase for a spontaneous process, or for any process, of course, because anything that is happening within our universe is spontaneous, because nothing else is actually acting on that from outside, because nothing else is outside and an isolated system. Therefore, in an isolated system, entropy increase is always favorable, because nothing else is driving. So, however, where is the statistics in breaking one egg? Or if egg falls and break, we don't get to see the reverse process at all. We don't get to see that the egg is joining back again. So the statistics is built not from macroscopic systems like cricket ball or an egg. The statistics is calculated on the tiniest, smallest ingredient of all species, atoms and molecules. So when we calculate this entropy on a molecular level, we're going to talk about atoms and molecules, not eggs and cricket balls, because they're too big to have statistics. While it requires only smallest number of variables, I already told you that, to describe equilibrium properties of a macroscopic system, it requires several variables, like in the order of 10 to the power 23, 1 mole. We can have 10 mole also, that will be like 10 to the power 24. But again, as you know, that this number is so big that multiplying by 10 doesn't really matter that much to describe a bulk system in order in terms of atoms and molecules. Once we know about the position and momentum of all particles, then we can obtain any property we like, and that is the fundamental assumption behind all this calculation. Even it is true for quantum mechanics. We need to know the position operator and momentum operator. Similarly, in classical mechanics, we need to know position and momentum. The subject which helps us to obtain is known as statistical thermodynamics or molecular thermodynamics. It is not possible, however, to know about this humongous number of variables. If I give you a glass of water, it will be impossible for you to actually count or say that what will be the position and velocities every instant of time. Therefore, a probabilistic approach is used in these calculations. Because when you don't know about so many possibilities, we can actually use probability to approach this particular problem. Although this approach will not give us individual detail, it will give us a desired property in terms of statistics. Again, similar to quantum mechanics. I will not delve into that right now. So thus, the connection between thermodynamics and statistical thermodynamics is probability, which will provide us an average expected outcome. Remember, average expected outcome. So statistical mechanics, why it is statistical? Because we are talking about averages. And why it is mechanics? Because we are talking about motions. Some people also say statistical thermodynamics. Why thermodynamics? Because we are going to talk about volumes, pressures, temperatures, everything. That's why we are calling thermodynamics. And why statistics? Because we are going to talk about averages, distributions. So you will see that how using statistics, you will be able to get all the desired thermodynamic, all the observable thermodynamic properties. Okay. So again, just to reiterate that why we need probability, that let us ask this question: will it rain tomorrow? Now, in order to really predict whether it will rain tomorrow or not, we need to know so many conditions like humidity, air pressures on a grid, and that's what atmospheric and earth and atmospheric scientists do. However, if we just use probability, then we'll just see that did it rain yesterday? If it rained yesterday, day before yesterday, and the day before, then what will be the probability that it will rain today? Or if it is a month of August or July, we need to know that from several years what is happening in the month of July, whether it is raining or not, and we can calculate a probability of having rain tomorrow. Although it may not be always correct, but on an average, it will be correct. So probabilistic approach is very, very useful while dealing with large number. Another important thing is that the statistics is more accurate when there are more sample points. For example, if we just talk about few things, like if I toss a coin, let's say only 3 times, the probability of head and tail will not be 50-50 because the statistics is too poor. So therefore, one has to really toss a coin for 1,000,000 times to find out that it is actually 50-50 or not. If it is not 50-50, you know that it is a biased coin. If it is 50-50, then you will know that it is an unbiased coin. So in order to know that, one has to do many sample points. And these casinos work on this probability. So when people go to casinos to play, let's say, gamble or in a slot machines, sometimes they may win. But however, the slot machines are designed in such a way that, there is a famous saying called house always wins. So the probability that house or the gambling house will win is 52%, 50.52 or 52%, and probability that all other people will win is only 48%. So on an average, if one person wins today, tomorrow, day after, but if that guy plays for a month, it is sure shot that that guy is going to lose. That is what statistics tells us. We don't have to really worry about individual detail, but we have to see that on an average, what is the outcome? And that statistics will tell us whether a process will happen or not. It is very important point. You may not get everything what I'm saying, but if you just remember that, then you will be able to connect that in future. Now, let us show you an example that why it is not always randomness that increases the entropy. So this is a work by Sharon Glosser, a famous scientist. What she did is that she took this kind of particles which are non-interacting, which means there is no energy bias between the particles. So there is no attractions, repulsions energetically. Okay. And this color red means they are disordered particles. Okay. So there is no driving force for the particle to become ordered. There is no energy or anything. Now, when she runs this system,
and as I start this simulation, you'll see by the that they start to align, they start to order with each other. And if we run it long enough, we see that this order starts to...
Okay. So I hope you got that. I'll play it once more. So red particle is disordered, green particle is ordered, and there is no energy bias. But what is happening is that spontaneously these disordered particles are becoming ordered. But you know that when there is no energy bias, then entropy is the driving force. So these particles are becoming ordered and entropy is also increasing. So this is an example where not randomness, not chaos, but an order increases the entropy.
And as I start this simulation, you'll see by the color green, which we use to denote particles that are ordered locally relative to their neighbors, that they start to align, they start to order with each other. And if we run it long enough, we see that this order starts to pervade the whole box. And this is because there are more ways for these particles to be. And as
okay, so this is from a TED Talk, and maybe you can search Sharon Glosser TED Talk, TEDx Talk, and you can listen to the whole lecture and also the related paper from that. Okay, so this is a very, very good example that even an order can increase the entropy. So it is not always randomness. So then the question is that, then why entropy increase is favorable? So I explained this particular one in terms of a very simple thing, that entropy is nothing but options. If you have more choices, more options, you have higher entropy. So imagine that you come to the class and the class is empty. You have 50 chairs there. You have an option to sit in all 50 chairs. The second person comes. That person will have an option to only sit in 49 chairs. The third person comes. That third person will have an option to sit in only 48 choices. And by that, we will know for a 50 people and 50 seats, how many possible ways one can arrange that. Now imagine you have 50 people and you have 100 chairs. Options will increase, right? Therefore, entropy also will increase. So entropy, you can always think about this particular thing, that whether the choice or options for any system or any process is increasing or not. When a particle gets evaporated, the choice of the particle is to be anywhere in the whole atmosphere. But when the like I'm talking about a bowl of water, let's say, for example, an open bowl of water. I was telling yesterday, right? If you keep an open bowl of water, then it will evaporate. After a few days, you will see the bowl is dry. That is because the water molecules, when it was in the bowl, it had only possibilities of moving within the bowl. But when it gets evaporated, then it can go anywhere in the atmosphere. So the options and choice for that water molecule has increased enormously. That means it's a higher entropy situation, and that's why it goes out. It favors that entropy against the energetic advantage that it had in the water in the water phase, where there was hydrogen bonding and interactions. So because the entropy is overwhelmingly larger in this particular case compared to the energetic interactions. Okay, so every system, if left to itself, will on the average change towards a condition of maximum probability. So it will, this is the statement, statistical statement of the second law. If you leave it, then it will try to attain the maximum probability or maximum choices that it can have. So again, just to say that, the connection between statistical thermodynamics and the actual thermodynamics, the classical thermodynamics, is that classical thermodynamics deals with bulk matter, and those are called macrostates, like number of particles, volume, and temperature. And statistical thermodynamics deals with position and momentum of atoms and molecules, which you call it macrostates. Okay, so, and as I told you yesterday, that Ludwig Boltzmann, almost on his own, and with the help of Maxwell's also, and then a little bit of, I think, Bernoulli, long back. So, but he came up with this particular equation, and this is his tomb where this equation is encrypted. So unfortunately, nobody believed him at that point, and he had to suicide. Or like people say that he had other problems. There is a debate about that, but it is at least famously known that Boltzmann suicided because nobody believed him at that point. This particular equation, just like Newton's equations of motion, is a postulate, and there is no equation that gives Newton's equations of motion. Similarly, this and Newton's equations of motion starts a new field called classical mechanics. This particular equation also starts a new field called statistical mechanics. It's a very, very simple equation. What it says is that entropy, you see, not delta S. We get delta S from classical thermodynamics. Here we are getting absolute value of entropy is proportional to logarithm of W, and W is the number of microstates. And proportionality constant comes out to be Kb. This is very important. This entropy thing is, you can find it in many, many places, in information theory and many other places, in machine learning, deep learning, a lot of places you will find this entropy word. It is proportional to logarithm of something. However, this Kb makes it realistic to be applied to our physical world. When you talk about waters or some reactions or all those things, this Kb becomes important. Again, you see, this Kb, of course, R, universal gas constant, is nothing but Na, Avogadro number, multiplied by Kb. So that's where it is connected. Universal gas constant came from experiment. And this Kb also can come from experiment. So, and they are connected, they are related, and they are universal constant, just like Planck's constant, universal constant. Okay, so now S equal to KBL and W is the equation given by Boltzmann, and this is the beginning of the statistical thermodynamics. Now, all that we need to show that when a process becomes more favorable, W increases, because then S increases. Then we know why a process is happening. In classical thermodynamics could not tell us that why entropy increases for favorable, but statistical mechanics tells us that entropy increase is favorable because it has more choices. See, let's say right now, all of you are probably at home. There is no school or something. Colleges are not functioning right now. So you have no choice but to be confined within your house. But as soon as, let's say, this pandemic situation goes over, you go to college, and then you can be anywhere. You can be at your place, all the way to the college and within the college and probably anywhere in the city. So suddenly you will have more choices. Some of you will, try to come to the class. Some of you will go to the library. Some of you will be in the cafeteria. Some of you will play. You have more choices. And when you have more choices, you will exercise those choices. Whether you want it or not, it will happen. And because it can happen, it is not that somebody is willfully doing something. Just because you have possibilities, it is happening. And essentially that means that is a high entropy situation because it has more possibilities. And that is the bottom line of the whole thing. After this, whatever I am going to talk about or tell you, those are nothing but quantification of this idea, like in terms of numbers. But the conceptual part is this, that if you have more options, you have higher entropy. Entropy is nothing but options. And this particular equation, how to calculate W and all that, will change with time. Now W is, it can differ for different types of systems and things like that. So I'm going to give you an example. Take any, distinguishable particle, although they are all red here, but imagine they are distinguishable and you have two boxes. Okay, so first particle you can put either in the left box or in the right box. So you have two choices. Second particle also you can either put in the left box or in the right box. So you have two choices. Third particle you can put in either in the left box or in the right box. So two choices. So for n particles, you will have 2 to the power n choices, right? So that means that the number of ways you can do that is, like, all possibilities is of course to the power n, but also you can take two, you can choose out of n particle, you can choose n1 particle to be on the left side or n2 particle to be on the right side. Let's say for one particular, okay, just 1 second. This is moving without this thing. Maybe timer is on. Let me just stop the timer. Presentation timer. Transition, slideshow, animation, slideshow, timer. Okay, I think this one on mouse. Okay. Yeah, so what I was saying, that the 2 to the power n possibilities are there. But let's say I tell you that you can only put n1 particles on the left side. So how many ways you can choose n1? That is a combination problem. Out of n particle you are choosing n1. It's called NCN1, n combination n1. And the formula of that is n factorial by n1 factorial multiplied by n minus n1 factorial. This you guys have studied in 12th standard mathematics, right? Combination, you have studied it. This is nothing but that combination. So now n1 can go from 0 all the way to n. And if you sum it over, you will get 2 to the power n. So this W is only one of those 2 to the power, this W is one of the possible distributions having n1 particles on the left hand side. But how many distributions you can have? You can have n1 can be 0, that is one distribution. N1 can be 1, that is another distribution. N1 can be 2, that is another distribution. N1 can be n, that is another distribution. So you will have n possible distributions, and one of them will be the maximum value, that is called most probable distributions. Okay, so I'll show you how options increases the entropy here. So more options means more entropy. Let's say I have 3 particles and there are 3 boxes. How many ways one can put it? Only one way, correct? So 3 out of 3. Now let's say I have 4 boxes and 3 particles. You can think of this as having an expansion process, that you have more choices now, right? So you can choose any 4 boxes for these 3 particles. How many ways you can do that? 4C3, so 4 possible ways. Now let's say you have 5. You see, every time your W, this is the W, increases. That means when you go from here to here, your entropy increases. So that means that if something is more packed, it will have lower entropy, but something is more free, you have more volume for the particle, it will have higher entropy. And that, so this is called lattice model, very simple models, but that can give you an idea that what could happen in the realistic situations. So what happens that, in physics, people typically try to construct a very simple model to understand a complex process, because essential aspects, once they understand, they can really go into more complex things. And this I got from a book by Ken Deal called Molecular Driving Force. Fantastic book. You can also look into that. And I told that yesterday also. Mixing of gases, you know, it is favorable, right? So again, lattice model example. Let's say there are two types of particles, and you have only like, you know, four boxes for each of them, right? Now you mix it. So right now there is only one possibilities, because 4C4 multiplied by 4C4. Now let's say you put one red particle here and one black particle here. You mix it. Now how many possibilities you can have for the red particle? Any of the four possibilities. Similarly for the black particles, any of the four possibilities. So 4 into 4 will be 16. Now you put two particles here. What will happen? 4C2 into 4C2, 36. So you see, when things are equally mixed, then number of possibilities increase. That means W increases, and therefore entropy also increases. And that's how we can show you that how entropy increase is favorable, because it has more W. So W increase is favorable. That's why ln which is entropy, is favorable. Okay, so this is when you actually join the box and make it bigger box, right? This was, let's say, V volume. Now you have a 2V volume in which two different particles, and if you calculate, you will see that it will have higher entropy. Now rubber band is another very simple example. You know, you can try this experiment yourself. So take a balloon, put the balloon on your finger, put it in, don't blow it up, just normal one. You can put it in your finger, stretch the balloon and leave it. You will see that the fingertip will become colder. And why it is becoming colder? And I'm going to explain that. So this is a polymer. So polymer means, you know, combination of monomers. And you see that when the polymer is completely stretched, when I stretch the balloon, it has only one possible way. So entropy is low. When it is, you know, completely contracted, then also the possibility is low. Only when it is somewhat in middle, then it has higher possibilities. So when you stretch it, it has a low entropy, and then you leave it. Because of high entropy, it shrinks and it takes the heat out of your finger because of that process, and that's why your fingertip becomes colder. Again, heat transfer. Why heat spontaneously transfer from, you know, hot to cold? That I'm going to explain probably using, again, very, very simple example. So let's say I have a system of total energy 4. Now, if I have a system of total energy 4, how many possible ways I can put, and all are distinguishable particles. So I'm putting 4 out of 10 particles on the upper level to have an energy 4. How many possible ways I can do that? 10C4, 210 possible ways. And how many possible ways I can put energy 2? 2 particles I have to put. So that is 10C2. So 10C2. Now, combination of that is a multiplication, because total entropy is entropy of A plus entropy of B. Now you know entropy of A is KB ln WA, entropy of B is KB ln WB. So therefore, when you sum them, then WAs and WBs will be multiplied. So initial system A and system B, when they are separated, then the total W is 9450. Now bring them together. What will happen? Heat will transfer from hot to cold. Now here the energy is 4. So therefore, you can put one of the particle to this side, so that energy will be 3 here and 3 here. Correct? So now right now you see that there are 3 particles. How many possible ways you can do that? 120. These also 3 particles. How many possible ways? 120. And when you combine them together, and you will get, again, SA plus SB, you will get 14,400. The previous one was 9,450. Now you've got 14,400. Now you see, entropy of A decreased, entropy of B increased, but together, when you heat is transferring from hot to cold, then overall W increases. And that is why heat will spontaneously transfer from high temperature to low temperature. And we can only understand that if we understand thermodynamics from from the point of view of the statistical aspects of thermodynamics. Then only we will be able to understand that, right? Okay, so I will skip this what is probability part because I guess all of you know that. So I will directly go to again the two-level system calculation. So you see again, as I said that since we're talking about statistics, we really need large numbers. So here we have constructed a system with two particles only, and these particles do not interact with each other. That means there is no energy involved in this. Now, ideally, what we would expect? We would expect one particle will be on the left box, another particle will be on the right box. But what happens is that this is such a small number, the statistics will not always play a role. And you will see often you will find all the particles on the left. Okay. And this bar shows that how many particles are there on the left and how many on the right. I can see majority of the time, it can be in this side or that side because number of possibilities is really low. Now let's take 210 particles. And you see when I started the movie here, all 200 particles were on the right box. And you see the bar diagram actually shows how many particles are there. As the time progresses, particles are going from this to this. And why they are going? Because there is no interaction involved. There is no energy involved. Nothing is telling them to go there. Then why it is going? Because it has more choices. It has now two boxes instead of one box. So that's why it doesn't want to. Doesn't want to stay there. It's not that anybody is forcing it to go. It is just it has more choices. And what is going to happen? You will see that more and more particles will go from right to left. And where they will stop? Where on an average, 105 particles will be on the left and 105 will be on the right. And that is the situation that will have maximum W. And therefore, that is the situation that will have maximum entropy. You can calculate that with 210. You will get 200 when the W becomes maximum, you will get 10 to the power 61 possibilities. So from zero situation when all the particles on the right, it will increase by 142.66 kb. So this is what is meant by when a system is left to itself, because nobody is touching the system, nobody is telling the particles to go, there is no benefit of interaction energy, yet what we see, the particles are going. And that's why it goes towards the most probable distribution, because that is what the most probable thing out of all possibilities. See, one possibility was all the particles on the right hand side. One possibility is all the particles on the left hand side. One possibility is that only 5 particles on the left and rest of the 205 on the right. Out of all these possibilities, which is most probable? When 105 and 105 on the left and right, that is the most probable situation. And our system goes towards that. And that is the beauty of statistical thermodynamics. We are not calculating heat. We are not calculating temperature. We are only calculating choices and probabilities. And we know that when there are more choices, there is going to be higher entropy. Okay, so this I will come to later on. Now how important it is to have more number of particles, I'm going to show you here. So here is the W, and this is the distribution of probabilities having 5 and 5 on the left and right. And you see that the distribution is quite broad. That means a left box having 2 particles and right box having 8 particles is also 5% probable, whereas 5 and 5 is 25%. But if you have 100 particles, the distribution becomes narrower. Now you see the percentage deviation from 50-50 is going to be less probable. And then when you have 1,000 particles, you see the distribution becomes even narrower. That means half is getting more and more probable. 10 to the power 4, narrower. And if you go really to very, very large number, we have not gone to 10 to the power 23. If we go to 10 to the power 23, you can see the distribution will be so narrow that there is only one possibility that will remain. That is this 50-50 possibilities. Okay, so percentage deviation from the 50-50 possibilities will be so small that you will only take that possibilities, and that's what we call as most probable distribution. See, I'll tell you. So when I was talking about particles having on the left and right box, then all possible distributions are there. Particle could be on the left and right, like 50 few particles could be on the left and the rest of the particles could be on the right. That is possible, but that is not the most probable situation. All possibilities are there, but the system left to itself will go to most probable situation, and most probable situation is when it will be half-half. And that's what is going to happen if you leave the system to itself, and if you have a larger and larger number of particles, then the relative deviation from this 50-50 possibilities is going to be very, very, very small. So what does it mean? It means that entropy is driving the system to attain equal number in both the boxes. And with more number of particles, it becoming more and more obvious. And you can see how small a deviation is there when you have 10 to the power 6 particles, 1 million particles. And you see for 1 million particles, a deviation of 0.2%. 0.2% is so small. Now imagine what will happen. See, so with a million particle, the deviation drops to 0.2%. Now with 10 to the power 23, 1 mole particle, a deviation of 0.000000002% will fall to 4.2 into the power minus 20. So that means you cannot even see this much deviation from the most probable situation. It is as beautiful and as robust as this. Although we are not really going through any of these atomistic motions and all that, we are only going by the probability and by calculating the W from a very, very simple equation for a two-level system, of course. And it still tells us that how difficult it will be to deviate a system from the most probable situation. And that's why most probable situation or most probable distribution is the only distribution that we are going to worry about while calculating entropy. Okay, so this is a Mathematica file just showing that how it will become narrow when you increase this W. That's it. Okay, so so now similarly, if you go from 2-level system to 3-level system, then we can calculate by the same formula. So let's say N1 particle on one box, then N2 particle in the second box, and N3 particle on the third box. So such that N1 plus N2 plus N3 becomes total 1. And you can do that and you will get this formula. This is called multinomial distribution. So the last one, when there are only 2 boxes or 2 level, we call it a binomial distribution. When you have 3 boxes, we call it a multinomial distribution. So, and again, what will happen? What is the most probable situation? 1/3, 1/3, 1/3. If there is nothing else is there. Again, when you do 10 particle, you will not see such a wonderful thing because small number. But let's now take 210 particle. What do you expect? 70, 70, 70. Now see, the simulation is running. It is, we have done this, but there are other this thing also. Okay, see. So I'm expecting 70, 70, 70. So all bars should become equal. Now it is going on. That means it is not in equilibrium yet. Once it reaches equilibrium, then it is going to remain 70, but it is going to fluctuate. So any deviation from 70 is going to go opposite of entropy, but that is okay because that is going instantaneously. But what statistical mechanics or statistical thermodynamics tells that on an average, it is going to stay there. So if you calculate that how many frames it will be there with 70, 70, 70, you are going to see that will be the majority. You see, it is going by itself. It is attaining a distribution. I have not programmed it to be like that. I have not told the particles to distribute in 3 boxes in this manner. We are just running a simulation where particles are free. They can go anywhere. There is no interaction or anything. And what we see? We see what thermodynamics does to us. We see a most probable situation attaining. And that is a formula, and that again, one can see that. But this, I should have shown it later on. What will happen if there is an energy? I'll come to that later on. So now let's say multi-level system. Now we are talking about fixed energy, and we know these are examples that often you find in quantum mechanics and in many other places. For example, we are talking about vibrational motions. So there is a vibrational quantum number, quantum states, and then H omega is the energy difference and all that. And we know that the energy, vibration energy, will be nu plus half H nu, and nu is the level. Now, nu can be 0, 1, 2, 3 and all that. Now, if I say that, okay, you have a fixed value of energy, okay, then what will happen is that there will be only one possible way to attain that. Similarly, but if you take two harmonic oscillators, then one can show that there are multiple possibilities. So let's talk about particle in a 3D box. So you know the formula for particle in a 3D box, right? So hs square by 8ml square, nx square, and z square, right? Now we know about the degeneracy of energy. Degeneracy means what? That how many possible ways one can have the same energy. For example, if the energy is 3, then there is only one possible ways, because you need nx, ny, and z all 1. But if the energy is 6, then we can have 3 possible ways. So you see, the number of possibilities increases when you increase your energy. So similarly, if you keep on increasing the energy, you will see that number of possibilities increases, which means that as the energy increases, entropy increases. And that has to be the case, because temperature is nothing but you know the dE equal to TdS, right? So T is dE by ds. So change in energy versus by change in entropy is the temperature. So if with change in energy, entropy change is also monotonic, then only the temperature will be positive. Otherwise, it will be negative, which is not possible by definition. So therefore, it can be shown that with energy change, entropy also change, and that's why it balances. In all our natural processes, we see that if something is energetically stable, entropy is also lower. Now, energetically being lower is more favorable, but entropically lower is less favorable. So they balance each other. So that always happens. Again, this is a 2 harmonic oscillator problem, and now we can have more possibilities. Now, if we fix an energy, you know that there are multiple ways to attain that, and therefore there will be a scope of having higher energy, and one can calculate those things also. I'll give you a simpler example though. So let's say I have a system, 4-level system. The number of levels are fixed, particles are distinguishable by different colors, and total energy is fixed at 3. How many ways one can do that? So this is one of the distributions where one of the particles is at level 3, and number of possible distributions. Sorry, I'll tell that later. So I can have these 3 possible distributions. You see, in every case, the total energy is 3. Here, one particle in the level 3, but here, one particle is in the level 2 and one particle is in the level 1, and here all particles in the level 1. Now, if you calculate that in each case, total energy is fixed at 3, but each of them has different W values. Here, the number of ways I can do this is 3, because any of the 3 particles could be in the level 3. Here, I can do it only one way, because all particles are here. So W is 1. But here, I can do it in 6 possible ways, because any 3 particle can be in the level 2. That gives me 2 more choices to put it here. So 3 into 2 becomes 6. So what is the most probable distribution? This is the most probable distribution. Distribution B becomes the most probable distribution. Okay, and one can calculate this probability of each distributions and show that this is the most probable one, because it gives you 6 by 10. Now I'll skip this particular part. You can find more detail in the NPTEL lectures, and I want to show you one more multi-level distributions where the total energy is 5 and 4 particles are there. Okay, so I put one of the particle in this. How many possible ways? 4 particles. So there are 4 possibilities. Now, how many possible ways? Out of 1, 2, 3, 4 possible ways to do this, and 3 possible ways to do this. So 12. How many possibilities for here? So 4 possibilities multiplied by 3 possibilities, 12. How many possible ways to do this? 4 possibilities multiplied by the 3 possibilities multiplied by 2 possibilities. So this is going to be the most probable distribution. And you will see, okay, so these also 12 possibilities are there, because we are actually living here only. So here you can see that all these 3 cases we have, they are all, or 4 cases, they are all most probable. But again, that's happening because we have only a very small number of particles and small levels. But once we increase this level to more and more, for example, 7 units of energy now, total energy is 7, there are 9 particles, and we can see that so many possible ways one can arrange them, and for each of them there will be W's which are going to be different. And if you look at, then this is the distribution that will have maximum number of W, and this means that this will have the highest entropy. Okay, and how to calculate that and all that requires more time, and I have explained that in much more detail in the individual lecture, so I don't have time here to do that. I'm not doing this. So again, multi-level at 300 Kelvin I'm showing. I wanted to show that a little bit later. Okay, so I'll just do one thing. I will put it here. Okay, so you see all these calculations I could do because I had very nice systems where equal energy spacing is there, number of particles are very fixed and all that. But realistically, energy spacings will not be equal, and one cannot calculate really how many distributions will be there and what is the most probable distribution. But, and for example, even for this particle in a box, you know that the energy spacings are not equal between the two levels. So in real situation, it will be even more complicated. So what are you going to do then? So we need most probable distributions. We know that we have shown that for large number of particles, most probable distribution is fine. Now one can show by derivation, which derivation is here, it is there in Atkins also, that when your total energy is fixed, then if you want to maximize the probability, then you will end up with something called Boltzmann distributions, where the number of particles in different levels is proportional to nothing but their energy differences. And once you have that, then you do not need to know how many levels are there. You do not need to know how many particles are there. If you just know the energy levels of a particular level E, then you know that the probability will be to the power minus E by kBT. So Boltzmann distribution rescues us from this situation or to calculate all possible distributions, and that is really, really helpful. So you see here now, when there is no energy bias, then what is going to happen is that, you know, particles are going to be distributed equally, right? That I have already shown. But when there is an energy bias, no, different box energies, this is also different. Okay, I think we have different energies in these particular boxes. You know, this box has lower energy. Just let me see if I have the right this thing. Okay. So this one, I guess this one has different energies in the boxes. Let's see what the distribution gives us. Okay. Sorry. Let's see what happens. So are they going to be equal or not? Let's see. Then we will know what is the situation. So I think I had also programmed in such a way that one of the box will have stronger energy, more negative energy. See? So this box has lower energy. This box has, you know, less than that, and this box has lowest energy. So therefore, particle is preferring this one, because Boltzmann distribution tells us that if it is lower in energy, it will be more favorable, and then this and then this. But it also tells us that at a higher temperature, that biases will be gone. So we have done that at a higher temperature now. It's the same, that this is lowest in energy, then this and then this. But you are going to see that what is going to happen, that at a higher temperature, it overcomes the energy bias and it is going to be flatter now. So Boltzmann distribution works fantastically. If you have all energies equal, then entropy is going to play a role. And if you have energy biases, then both the energy and the entropy together, which we know as free energy, is going to finally determine what is going to happen. So you see, at a higher temperature, it overcomes the bias, and more or less all of them will be similar. Okay, so yeah, so now coming back to the distribution of energy, I think in the first class yesterday I talked about that distribution of energy is entropy, right? So I'm going to just show that. So I already calculated the W here, and W here, right? We already showed that for 3 particle situation. Now, if I calculate the distribution, what I'm going to see that all particles are in level 1. So distribution is very narrow for this particular case. So W is less, distribution is narrow. Sorry. Yeah. Then what I'm going to see here is that distribution is little bit better, more flatter here, but not as flat as this one. This is the highest W and most flat distribution, having the highest entropy. So what is the conclusion? So in all cases, energy is same, but this situation, the entropy is maximum. Why it is maximum? Because the distribution of energy is flatter. So now what we know, that it is the distribution of energy that governs the entropy. Energy is always fixed, but as it distributed more and more flat manner, entropy is increasing. So in our real world, all that is happening is that with time, the energy distribution is becoming more and more flatter. So I think this is what the Boltzmann distribution shows, and there are more complications there, but I would not go into that. For example, when you talk about Boltzmann distribution, we talk about only the indistinguishable particles, but then when you talk about bosons and fermions, and then we talk about Maxwell-Boltzmann is for distinguishable particles, but when you go to bosons, they are indistinguishable particles. Fermions, they are indistinguishable particles, but having the property that how many particles will be in one particular level or not. And you will see your boson, fermion, and Maxwell-Boltzmann distributions are going to be, coming out from this same calculation. So maybe if I have time, I'll go through that. So where I was here. So the Boltzmann distribution is, I already told you that E by kBT, and then I get this because I maximize W under these constraints. I already told you, did not show you the derivation, but one can do a derivation and one can find out that if you want to maximize W under these 2 constraints, then you are going to get this equation, and this equation is nothing, and B is nothing but 1 by kBT. So you're going to get Boltzmann distribution like this one for distinguishable particles. But what happens if the particles become indistinguishable? If that happens, you have a different calculations. This you ignore it. I already showed you what these situations will be, and one can calculate the statistics from there, and that I have done, but forget about that. Let's go to other type of particles, distinguishable and indistinguishable particles. Let's go to indistinguishable particles. So bosons. Now bosons are indistinguishable, but any number of bosons can go into one particular level. So again, I colored them all blue because they are indistinguishable. Now you can see that how many possibilities are there. All of them are 1. Because they're indistinguishable, you don't know which one you are putting at 5. So all are same, all W's are same. There is no differences. Similarly, here also you can calculate all W's will be same, and one can calculate a distribution. For fermions is even more complicated because fermions can have either 0 or 2 in the one level. So this is even not allowed because there are 3 particles here. This is also not allowed because there are 3 particles here, and therefore you will get again certain number of particles at a certain level, and you can calculate the boson distributions. And finally you can actually plot both the fermion and boson. So this is the formula for fermionic distribution, and there is a formula for bosonic. This is a formula for boson distribution. This is the formula for Maxwell-Boltzmann, and this is the formula for Fermi-Dirac. And you can derive all that from very, very simple models. And I think with that, I will end it. I am ending it a little early so that if you have any questions, we can discuss them. Okay, so thank you very much. So now I think I will stop the presentation, and you can discuss further if you have any questions.
Participants can ask your questions.
Okay, I see in the chat box.
Students, you can ask directly to sir, or you can type it in the chat box.
Yes. Yeah, so maybe, I don't know how many of you are in the postgraduate level MSc, and I don't know whether is statistical thermodynamics is there in syllabus in the MSc?
Yes, sir. In
Okay.
MSc, it is there, sir.
Okay. Okay, although and as you have seen that I have really not used the equations at all, because I try to be more pictorial in terms of presentation, and these things takes time, because this I just wanted to give an overview, because if I have to explain it in each detail, it will not be possible to do it in 1.5 hours. So I just wanted to show that what can be found in my NPTEL lectures or in some of the books that I mentioned.
Madam?
Oh, yes, sir.
Yeah.
Is there any question in the chat box?
No.
Okay, so if there is no question, then also there is a possibility that I'm just in the chat, I'm giving my email address, and if they want, any of the student wants, they can send me an email directly with the question. Maybe the question will come later on once they sit with it. Question may come. So whenever, feel free, don't hesitate to write to me directly if you have any question. Just tell that you are from this college and which topic or which part you want to understand better, and I can refer to you either books or part of my other lectures to study on that particular topic.
I think students will ask you questions directly to you, sir. And another thing, it's a vast area, and then people want to just go into that, and then only they will be in a position to ask.
Sure. No problem at all.
Yes, sir. So now, actually, I would like to thank you, sir. Gratitude is a quality similar to electricity. It must be produced and discharged and used up in order to exist at all, said by William Faulkner. Actually, saying thank you is more than a good manner, it is a good spirituality. Hence, I stand before you to express our sincere thanks for giving wonderful 2 days lecture on basics of thermodynamics. Though thermodynamics started almost 200 years ago, even today it is in the forefront of scientific and technological development, and in its applications in quantum objects to biological systems and stars and galaxies. Actually, you have completed a marathon race in a 200-meter dash time, sir. But yet you have done it in a lucid manner, and really it is wonderful, sir. And just as the constant inverse of increase of entropy is a law of the universe, so it is the basic of law of life to be ever more highly structural and struggle against entropy, said Locke Havel. So here actually this thermodynamics is very useful. Actually, students feel its difficulty only when they don't know the mathematics. But if they know the mathematics, actually in thermodynamics is a beautiful subject, and then you have covered from the scratch to the statistical, from classical thermodynamics to the statistical thermodynamics in a great manner, sir. We are very, very much thankful to you. And then actually you have beautifully in a simple manner explained the difference between the statistical thermodynamics and the classical thermodynamics. And with all animated pictures and other things, definitely students will be having their, it has kindled interest in the thermodynamics, it would have kindled interest in the thermodynamics, and students will definitely study more and more in your, from your NPTEL lecture, because it has initiated some interest, and then definitely they will look into it. Because covering such a big portion within 2 days is really great, and you have done justification for that, from starting from the basics to the statistical thermodynamics you have done, and it is a very wonderful thing, sir, and we are very much thankful to you for giving such a wonderful lecture. And in the near future, after this pandemic is over, we would like to have you in person in our college, sir. That's
Sure,
what we
definitely.
and let the pandemic get over soon. We all pray to it, and then we are very much thankful to you, sir. And then I would also like to thank our secretary and correspondent and principal for giving this such a wonderful opportunity, and our HOD for arranging such an eminent person for the benefit of the students, and all our faculty members and other faculty members from other colleges and student friends for attending this webinar. Thank you, one and all.
Yeah, so just one question is there. I will just try to answer that question.
Yes, sir. Yes.
So the question is that what are the limits of the definition of thermodynamic entropy for macroscopic systems which aren't in thermodynamic equilibrium? So as I said, that the system has to be in equilibrium. That is the condition to talk about thermodynamics. That is the first condition. But it is applicable for a big system. Like, you cannot talk about thermodynamics with only 2 particles or 3 particles. When you talk about thermodynamics, you are talking about a mole of particle, which has 10 to the power 23. These are the 2 conditions. If it is satisfied, then you can apply both classical and statistical thermodynamics.
Hello, good afternoon, Dr. Arnab. I'm sorry I couldn't attend the lecture today. I was in a meeting just now I came.
Recording will be available.
Yeah, we have recorded. I will go through it, and thank you so much once again.
Can you also send me the link? Can you please also send me the link?
Definitely. I'll send it to you, sir.
Okay. Thank you.
It is streaming in YouTube also.
Thanks a lot.
Okay. And it's also my pleasure to again, be in touch with you, all the teachers, and also the students. It is my, I always, feel great when I get the opportunity to talk about, teaching subjects rather than research. Research, anyway, we give a lot of lectures, but we don't get many opportunities to talk about our teaching subjects. So thank you for giving me that opportunity, and thank you for initiating this interaction, which will probably be very beneficial for mutually beneficial for both you and for me as well. So,
yes. So, with your permission, may I ask I can say my Guru, Dr. S. Vadalakshmi. She is a retired professor of our department. She has attended both of your lectures. I requested her. Let me ask her to say a few words.
Sir, good afternoon, sir.
Good afternoon.
Very lively lecture. So I retired from the same department.
Okay.
I used to teach physical chemistry for many years. But so you have made the more disordered entropy to the more orderly one. So through your presentation, so very nice, sir.
Thank you.
All your the simulations, it went on so well with the subject. So you could definitely you have increased the visualization of our students. So thank you so much, because in our time we never had the facility for using all these simulations and all. Okay, with chalk and talk only we could manage everything. Whereas with everything you have done it very lively. So made it so lucid, nice presentation. So wishing you all the best, sir.
Thank you very much.
Looking forward to hear your lecture.
Yeah, thank you, madam. It was my pleasure.
Thank you. Nice. Nice, Ariel, for giving the nice opportunity to all of us.
Thank you, ma'am.
Here to such a nice lecture. Thank you.
Thank you, madam. Thank you.
Rangasamy, sir?
That's it, madam. You can close it.
Okay.
We are at the end. Okay.
Okay, thank you. Probably we'll see you soon. Okay.
Definitely.
Okay. Bye. Okay, so feedback form is there. So also kindly send me the feedback once you receive it.
Feedback I'll send the recording also, sir, the link also.
Okay.
Definitely.
Okay. Thank you.
Thanks a lot, sir. Thank you.
Thank you all. Bye.
Thank you, sir. Bye.
period table. Chitra இப்பதான் வராங்க.
Live at close பண்ண சொல்லுங்க எழில்.
Shankar sir, you can start streaming.
Ma'am, good afternoon, ma'am. Swarna Lakshmi. Yes, sir, ma'am.
Shankar sir, light stop.